Hi all, thank you very much for tuning in to my channel on ozone technology. This session is session 7A. I will be dealing with ORP and finishing that topic which I introduced in last session, and then introducing polarity, solutions, type of solutions, and ionization. Recalling the redox potential and its significance, you will note that the redox potential is simply a measurement of the oxidizing capacity of a chemical. It is measured in millivolts or in volts, which is less than 2.5 or 3. The redox potential is related to the oxidation of the medium. The higher the oxygenation, the higher the redox potential. The higher the redox potential of an element, the higher oxidizing capacity of that element. The positive redox potential indicates the element's oxidizability, while the negative redox potential indicates the element's reducibility. I'll refer you to the diagram on the right side of the slide. You would note that I did explain to you between A and B, where A being oxidized to an oxidized A, B being which oxidizing agent is reduced to reduced B. So the diagram here shows that when oxidizing agent B oxidizes A, the electrons are removed from A and transferred into B, so that A becomes an oxidized chemical, while B then becomes reduced chemical. Now, with respect to the ORP, now if you find the ORP in, say, in water, for example, below 100 millivolt, then it could give you an indication that it is an anaerobic environment. And if the redox potential increases, then as during oxygenation, then the anaerobic status will become aerobic. And redox potential above 700 millivolts in a liquid, generally water containing the chemicals, will ensure the killing of all bacteria and inactivation of virus. This slide shows a relationship between the effect on E. coli of an ORP. If you look at the right side of the chart, that is at the x-axis, you find that at about 600 millivolts, the kill time, if at all, is about 100 minutes, rather 100 seconds. However, if you increase the redox potential, say from 500 to 600, 630, 700, and 700 plus towards 720, you notice that the kill time of E. coli reduces from the 100 seconds to about, if you look at, because it's logarithmic, it is about 6 seconds. So within 6 seconds, if you have a voltage or redox potential of above 700 to 750, E. coli is killed. Whether you use ozone or whether you use chlorine, the actual time of kill will be relative, because the maintenance of the ORP above 700 and 720 is dependent on the strength of the oxidizing chemical, whether it is ozone or chlorine. So if we, in the reaction of sterilizing the water, if we are able to raise the ORP to above 700, maybe 800, and keep it for 5 minutes to be sure, rather than 100 seconds, you will be certain that all the bacteria will be killed. This slide is only representing the fundamental bacteria, which is very reliable source to show the relativity of kill time. But this would apply to all the other bacteria. Now I would like to introduce you to the principle of the ion exchanger. Now you will notice that water, when it contains very high levels of dissolved solids like calcium and sodium, potassium, etc., and particularly calcium and carbonate, and bicarbonate, which gives the water the hardness. The only way by which you can soften that water is to remove the calcium and bicarbonate. Normally, you cannot expect oxidizing chemicals like ozone and chlorine, etc., to remove it. This will also apply where the water has got too much salt and you want to try to remove the salt. Now, this exchange column, which I'm referring in this diagram, is used to remove the sodium chloride and others. For example, when they prepare deionized water for battery solutions that which you find in the supermarket, what they are doing is removing all the negative and positive ions, including sodium chloride and calcium, potassium, etc., and all the negative ions, chloride, sulfide, nitrite, etc., so that what remains is only the hydrogen ion and hydroxyl ion, which will be pure water. The ions, there are two types of ions. You have the cationic ions and the anionic ions. The anionic ions are ions that will selectively exchange negative radicals with 4 hydroxyl grouping, and the cationic resins will exchange the positive ions and release the hydroxyl groupings. That means it takes away the sodium chloride or sodium sulfide or sodium nitrite, etc., and will release the hydrogen and hydroxide radicals, which gives you water. When the the resins are depleted, we normally recharge it using brine. And then we can use it again. We can use the other for cationic resins, anionic resins, use strong brine, and for cationic you use strong hydrochloric acid. This diagram shows the use of a mixed bed. In other words, they are both anionic resins as well as cationic resins, within the same column, so that as the water, hot water say flows, slowly there is an exchange of the cations for hydroxyl, hydrogen ions, and the anions for hydroxyl ions. So by the time the water flows back into the outlet, you will find most of the ions have been exchanged, so that you will have only a soft water or deionized water that is left. So this will be also the columns they can use for deionization instead of two separate columns. So it's more convenient, because in recharge you can recharge one at a time using brine for the sodium and the hydrochloric acid for the hydrogen. I'm introducing the subject of polarity because whether one element or one chemical reacts with another will also depends on its polarity and other characteristics. It will be useful for you to know this when dealing with reaction of ozone with other chemicals and other elements. All molecules will contain basically three components: the positive, which is a proton, a negative, which is an electron, and neutral, neutrons. When there is an equal distribution of protons and electrons in the molecule, that is an equal distribution of a plus and the minus, and therefore it is neutral. And it also becomes bipolar. That means it's not liking any positive or negative ions. If there are more electrons than the protons in the molecule, then the molecule is polar and is negative, and therefore it tends to go towards the positive chemicals. Neutrons and the protons will determine the molecular weight of the molecule. So if you have more neutrons and protons, the molecular weight will increase. So periodic table will show exactly each of the elements which are respective proton electron configuration and the amount in the molecule that determines the molecular weight. Example, where hydrogen is the lightest and uranium is the heaviest. Hydrogen has only got one proton, and uranium has got very many protons and neutrons. Therefore, that contributes the weight. A polar molecule is attracted to a magnetic force. As I did mention to you, if it is negatively oriented, it will go into the positive pole of the magnet. And it is positively oriented, it will go to the negative pole of the magnet. Polar molecules also attract or repel each other. In other words, the negative will repel the negative, and the positive will repel the positive, depending on the polarity, and are soluble in polar solvents. Non-polar molecules such as fats have no attraction and will dissolve in non-polar solvents only, and it will not dissolve in polar solvents. So this information is useful when we are dealing with polar and non-polar substances. In summary, a dipole is anything with a positive end and a negative end. Another word for it is polar. A bond is a dipole if it connects different atoms. A polar molecule or dipole is a molecule where the polar bonds are asymmetrical, not symmetrically arranged. The dipoles do not cancel. A non-polar molecule is a molecule with no polar bonds, or a molecule where the polar bonds are symmetrically arranged. That is, the dipoles cancel. If you want more information on this polarity, I would strongly recommend the presentation by late Laurie, for which I'm given the web page. We will now introduce you to the principle of solutions and colloidal solutions. So there are two types of solutions. One is a true solution and the other one is a colloidal solution. A true solution is, for example, is a solution of sodium chloride in water, in which case the sodium dissociates to sodium positive and chloride negative ions in the water, and it is electrolytic. This is a true solution. In this case, in order to remove the solids from the solution, there are only two methods available. One is to evaporate the water completely to get the residue, which means and then of course you can recondense that water. And the other, of course, is to remove it through ion exchange. But in ion exchange, you will not recoup whatever you have taken out. Now, the chemicals that are formed through solutions, for example, are almost all chemicals that are strong, between a strong base and a strong acid, like calcium chloride, sodium sulfate, potassium chloride, etc. And because of the dissociation between sodium or positive ions and negative ion, this solution will conduct electricity. A colloidal solution is not actually a true solution, but it's a mixture of very, very tiny particles, so tiny that it will pass through most of the filters, but it's not small enough to allow light to flow through. In other words, colloidal solutions do scatter light. For example, proteins or inorganics such as ferric hydroxide, etc., are good examples of colloidal solution. Another good example is milk, where the milk protein in the water is small enough to pass through all the filters. An example of inorganic colloidal solution is colloidal silver. Nanoparticles of iron also can be classed as colloidal iron. Now, as you know that both the solution and colloidal solutions both pass through the filters, so it is very difficult for you to separate a colloidal solution. It is difficult to separate the contents of the colloidal solution as you would do on a solution. So there are methods by which you can separate them, and these are the things that will be dealt with the next slide. As we mentioned colloidal solutions, now we have a procedure by which we can remove the colloidal solution from the water, and the process by which we do is called flocculation. There are In the case of chemicals that form colloidal solutions, we call them chemical coagulations. And where in the case of protein dissolved in water, such as milk, etc., we call the flocculation denaturation. What actually happens in both coagulation and denaturation? With respect to the coagulation, for example, when we use the coagulation to remove lots of dissolved sediments, fine colloidal particles in water, we add alum. Alum becomes a gelish substance, and that will bind to the organic material in the water, and when you add the appropriate chemical, it immediately flocculates so that it can be filtered off, or it will settle. Now, in case of a soluble protein like milk, etc., albumin solution, etc., all you have to do is denature the protein. And denaturation of a protein is very simple. You just alter the protein molecule by either oxidation or reduction or reaction, which one of the particles or one of the linkages in the particle, and suddenly the nature of the protein changes and it sediments. And this is called flocculation also, and by denaturation of the protein. Ionization is the process whereby the cation and the anion separate from the main chemical in the presence of water. For example, sodium chloride in the solid form is bound to each other, sodium and chloride. But when you put the sodium chloride in the water, the sodium and chloride separate. So sodium forms sodium positives and chloride forms chloride negative in the water. So which means these positive and negative ions will be able to carry electrons from one metal to another. So therefore it can conduct electricity. Solid bleach, for example, sodium hypochlorite dissociates to sodium plus and OCl minus. Solid bleach dissociates to calcium plus and OCl minus. Substance also that ionize conduct electricity. The greater the ionic content, the greater the conductivity. So this conductivity can be measured, and from there we know how much of negative ions or positive ions in the water. For those people who are very much interested in reading more about ORPs, denaturations, coagulants, etc., please refer to the reference I've given you in this slide. I've also put in reverse osmosis, but this will be discussed in the next slide because I'm running out of time. Thank you very much for having the patience to listen to this session. This is the end of this session, session A, 7A. Please go to the next session, 7B, for further informations on fundamental chemistry and parameters for ozone applications. If this is your first tune in, please visit session 1 and 2. That will give you the complete program details. And then, of course, sessions 3 and 7A that has already been published. And I would appreciate if you click the like icon and the subscribe icon. And if you do that, you will be notified of any future slides and sessions that I would be introducing. Please note that I'm attempting to introduce one session every week. And thank you very much for listening and viewing. And I would like to say good day to all of you. Thank you.